Bonjour! Today we're going to look at one last method of differentiation that is particularly helpful when dealing with complicated functions involving products, quotients, and powers. And I want to show you an example of a function where this is going to be really nice. Let's consider y equals the whole thing x to the 3/4 power times the square root of x squared plus 1 all over the quantity 3x plus 2 raised to the 5th power. Now, this is nasty. Nobody wants to differentiate this using the rules that we know, because if you look at this, we're going to have to use the quotient rule because this is one big quotient. But then in the denominator, we would need the chain rule because we've got an expression raised to a power. But then in the numerator, we would need the product rule because we've got a product. And then on top of that, we would need the chain rule for the part that's under the radical. All right, that's just going to be awful, but we can make things a lot easier if we take the natural log of both sides and then use implicit differentiation, as we've been doing recently. So let's take the natural log of both sides. On the left-hand side, that's just going to be ln of y. On the right-hand side, that's going to be ln of this whole big dang fraction, x to the 3/4 times the square root of x squared plus 1, all over the quantity 3x plus 2 raised to the 5th power. But you might notice something here. We can split up this logarithm. Remember that when we have the logarithm of products and quotients, we can split that up into the sums and differences of logarithms. So we could write this as ln of x to the 3/4 plus ln of the square root of x squared plus 1 minus, because it's in the denominator, ln of 3x plus 2 raised to the 5th power. But we can do even more, because remember, when we have the log of something raised to a power, we can pull that power out front as a coefficient. So I'm going to rewrite ln of y down here, and I want to look at all of these expressions and pull the exponents out front. So for this first one, we can pull the 3/4 out front. So that's going to be 3/4 times ln of x. Now for the next one, we've got a square root, but we know that the square root of an expression is the same as raising it to the 1/2 power. So we can pull that 1/2 power out front, and we've got 1/2 ln of x squared plus 1. And then we've got minus, again, we've got an exponent that we can pull out. We pull that 5 out front, and that becomes 5 times ln of 3x plus 2. And now that we've taken the log of both sides and we've used the laws of logarithms to split up and expand what we have on the right-hand side, we can use implicit differentiation, and it's really not going to be that difficult. All right, so let's differentiate both sides with respect to x. All right. I'm just going to rewrite all of this with d over dx out front. All right, you can pause the video if you need a moment to write that down. So let's differentiate both sides. On the left-hand side, the derivative of ln of y is 1 over y, but then times y prime, because remember, we're differentiating with respect to x, and y is a function of x, so we've got the chain rule there. Now, on the right-hand side, if we look at these three pieces separately, when we differentiate 3/4 ln of x, that's just going to be 3/4 times the derivative of ln of x, which is 1 over x, plus 1/2 times the derivative of this logarithm. Now, we're going to have to use the chain rule here, but it's not that bad. The derivative of ln of u is 1 over u, so that's 1 over x squared plus 1, times the derivative of the inner function. The derivative of x squared plus 1 is just 2x. And then minus 5 times, again, we have to use the chain rule. The derivative of ln of u is 1 over u, so that's 1 over 3x plus 2, times the derivative of the inner function, which is just 3. Now, we can clean up things on the right-hand side, but I want to do one other thing at the same time. Remember, we want to get y alone, so we've got to get rid of this y in the denominator. So I'm going to multiply both sides by y. So when we do that on the left, we get this y prime on its own. And then on the right, we have y times all of this. But let's clean this up. 3/4 times 1 over x is 3 over 4x plus, well, we can see that the 2's are going to cancel for this middle bit because we've got 1 in the denominator and 1 out front. So that leaves us with x in the numerator over x squared plus 1. And then minus 5 times 1 times 3 is 15 over 3x plus 2. Now we're almost there. There's just one more step. All of this derivative is in terms of x, except we've got a y out front. But remember, we already know what y is in terms of x because that's what we started with. So the very last step is to just substitute back in our original function for what y was. So this is going to be x to the 3/4 times the square root of x squared plus 1 all over the quantity 3x plus 2 to the 5th power times everything in that other set of parentheses. So 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that is our derivative. That is our y prime. Now, I know this result doesn't actually look nice, but the calculations that we did are much simpler than using the quotient rule along with the product rule, along with the power rule. In fact, the textbook that I originally used when I was first teaching this referred to that calculation as horrendous, whereas this is a lot less horrendous. So I just want to quickly share what the steps are, kind of a summary of what we've done here, because we're going to be able to apply this to other problems as well. All right, so let's just quickly review what we did. We started by taking the natural log of both sides. That's what we did here, ln of y on the left and ln of that whole beast on the right. Then step 2 says use the laws of logarithms to expand the right side, assuming that the right side is the complicated one. So we took all of this in the logarithm and split it up into multiple logarithms with the exponents pulled out front as coefficients. Then you can differentiate implicitly with respect to x. Because you've split up everything on the right-hand side, that gets rid of the requirement of using the product and quotient rules. And then once you've done all of that differentiating, you need to solve the resulting equation for y prime, which basically is going to involve multiplying to get the y on the right-hand side, and of course writing it in terms of x. So it is a lot of work, but it is still much nicer than using the quotient and product and chain rules all together so many times.